Good afternoon, everyone. So for this week, we're talking about classification methods for data. So on Monday, I just showed you a couple videos looking at different visualization methods. Give you some tips as far as like color choice goes, and just some stylistic tips for making your maps more aesthetically pleasing and effective in general. So for lab this week, we're not actually making any maps. We're creating some visualizations. These charts are also visualization. But you should think about those stylistic tips down the line when you're making your maps for Module 5, for instance. Because you can have the best analysis ever, but if you can't convey your results in a clean and concise manner, it really does not matter. So what we're going to talk about today is just different ways that we can group classified data to simplify it so that we can find patterns that we might not be able to find immediately just looking at the raw data itself. It's often useful to take data, especially when you have a large number of data points, and simplify it so that you've got 4 or 5 classes to look at. So we're going to talk specifically about these 2 different classes and types of classification methods. We've got supervised and unsupervised. So supervised are where we have more say or input in what's going on, and unsupervised is mostly just letting the data define itself. But before I cover these methods, I just want to talk a little bit about statistics and data manipulation. So these terms might be very familiar to some of you, and for others it might be, like not very familiar. You might be like, oh, statistics, no. So that's one of the difficult things about teaching a class like this, where people come from such a wide range of backgrounds and disciplines, is like I don't really know how to tune it necessarily in terms of like what experience everyone has with things. So I just wanted to cover some stuff that might already be pretty familiar to some folks, just so that we can kind of all be on the same page at least a little bit. So before you ever start classifying your data, it's important to just look at it to see what the distribution is. So in Module 3, I had you look at the histogram of the NDVI values, and you could see kind of clearly on it where the water was at one peak, and then the other sort of tail was the more green vegetation. Histograms are a really useful tool, regardless of, well, not regardless of, but generally speaking, histograms are a useful tool for looking at the spread of the data set when you're working with numeric data. So what we do with a histogram is we just order the data, and then you group it into bins. So you say, I want to look at 10, 15, 20, 30 bins, right? I think ARC by default does like 26 or something. Anyway, this is just a histogram showing the distribution of income, which is one of the values that you downloaded. So distribution of income by census subdivision in BC. And so this histogram can give us some information about the data set. First, we see that there's a large spike at the very low end, right? And we see that there's just a few points at the very far end, but we also see that most of the data is kind of clustered around the mean. We also see the mean isn't the most frequent value. And so the histograms will have very different shapes depending on what value you're looking at. So it's pretty easy to create a histogram in ARC. If you, so this histogram, for instance, is showing the distribution of income that people spend on food. It's a very different shape than if you say look at histogram of population, right? So selection, you can tell it to display like different things on here if you want, or you can just have it as its own. But right, you see the distribution of population, for instance, looks a lot different than the distribution of food costs or income. So it's just important to use, and I guess I don't know if I've had you all create a histogram for a raster data set. We can do the same for vector, right? It's really easy to do. You just go to create chart and then you click on histogram. So histograms are really useful for just inspecting the data, getting just your kind of first look at it and seeing, okay, this is what the central tendency of it is. It helps you spot outliers. I'll speak in a moment about that. But that's usually a good first step, is to look at histogram. Building on that, you want to take into consideration some other measures or metrics, depending on what kind of data you're working with. So measures of central tendency, that's mean, median, mode, are most useful for quantitative data. If you think back to last week, I think it was, or week before last, they gave you that little table of different operations that you can do on different data types. And so for quantitative data, that's interval and ratio. Anything that's numeric, you can always calculate the mean and the median. They're important values to look at, right? Just like where's the middle of the data set. And one key distinction, the median is just the middle value of a ranked or ordered set. It's not impacted by outliers, whereas the mean is just the sum of all the values in the data set divided by the count is impacted by outliers, because if you have one that's way far out from the data set, but it's a really high value, it will pull the mean in that direction. And then we've got the mode, which is just the most frequent value in a data set. Now the mode is not useful for continuous data. So that's things with decimal points. Or generally speaking, it's not very useful. Typically, you don't really want to calculate the mode for numeric data. You can do it with discrete numbers. But the mode is something you can use for qualitative data. So it's important to just think about where's the middle value in this data set. And these descriptive statistics can be used to either guide your choice of classification method, or in many cases, they are used as inputs by the classification method. So you also want to think about measures of dispersion, not just where's the middle of the data, but how does the data spread. So a simple one that I'm sure everyone kind of is familiar with is the range. It's just the difference between the maximum and minimum, right? How far apart are they? The farther apart they are, the greater the range. Then we've got standard deviation. So you can see that up here on this histogram. Standard deviation is just a measure of spread around the mean. It's calculated by summing the difference between every single value and the mean, squaring those differences, then dividing it by the number of values and taking the square root. It's a very common metric used in statistics. A lot of people struggle with it when they first are introduced to the idea. I'm not going to make you memorize the equation for standard deviation. That's what Google's for. But if nothing else, just know that it's like a measure for dispersion around a mean. And the reason it's called the standard deviation is because it's a way to standardize it so you can compare between different data sets. I've got another thing called the interquartile range, which I briefly mentioned when talking about box plots, but I'll just create another box plot just to kind of emphasize that point. So let's just look at a box plot of income, for instance. So I'm going to change the axes label just to make it a little What the interquartile range does, if you highlight over here, it shows you a bunch of different statistics. So the box plot shows the range for spread of values by the top tick mark and the bottom tick mark. So those are the maximum and minimum. But the actual box part here is the interquartile range. And so what that means, quartiles are just quarters, percentiles, so 25th and 75th percentiles. It's just the difference between the 75th and 25th. So it's another measure of the spread or dispersion of a data set. It's not particularly impacted by outliers, whereas the standard deviation and the mean are. Then we've got known as like frequency distribution. This is more useful for categorical data types. Sometimes it can be used for discrete numeric data, depending. But it's just like the distribution of counts within a data set. So if you're working with categories, for instance, if you're working with the urban rural class, you want to know how many subdivisions are rural and how many are urban, right? It's important to look at the frequency distribution. Bar charts are great for looking at frequency distributions, things that have counts. Then you've got probability distribution. This is a bit more complex. The most common one you'll see talked about is the normal distribution, but there's essentially infinite possibility, different types of probability distributions. Again, I'm not gonna like drill you on this, but I want you to understand the general idea. So like the normal distribution, you've probably heard of, the bell curve, is just an idealized distribution, and it's based on the distance from the mean in standard deviations. So the way this works is it's like 64% of all values will fall in the red, 96-ish in between the red and the blue, and on from there, right? Now this only applies if the data is somewhat fits that normal distribution. So if you're looking at this histogram, it doesn't really fit the normal distribution. So just pull this up. If we look at the percentage of income that people spend on food, this is the normal distribution really well. If we look at the population, it does not fit the normal distribution at all. So this doesn't work for things like counts up. I mean, it will in some circumstances, but if it is a ratio data that just starts at 0 and goes up, and all the data is clustered near 0, it can't really have that other tail in the normal distribution. So there's lots of other distribution types. I'm not going to belabor that point, but I do want you all to be aware that it's important to look at the distribution of the data and think about how it's distributed when you're trying to think about how you might want to classify your data. But also, a lot of these algorithms themselves are based on this. So another thing that we've done a couple times now is data normalization. And I talked about it a little bit when I was introducing data types. I talked about that derived ratio. But data normalization is a really important step in a lot of situations. It's not always necessary to do, but in a lot of cases it might be. So it's always important to think about and at least consider doing. And so there's a number of different reasons why we might want to normalize our data. What it allows us to do is a couple different things. So we could scale our data. Normalizing allows us to scale by the units of another variable. Calculate rates, for instance, so like time, area, population. These scaled values are often more meaningful than just the raw values. So a good example is COVID case base. So COVID cases, just looking at, say, provincial totals is not really that useful because the population of the different provinces and territories are vastly different. You've also, I'm sure, heard of the rolling average 7-day metric is better than the individual day, right? Because that can average out some of the inherent variability in daily cases, right? So if you look at like the 14-day count of cases on this data portal that the government has put out, I mean, you can see that Alberta is a catastrophe just based on this, but it doesn't really contextualize things very well, right? We're just looking at total counts, and on the map you see area. If you're familiar with like the general spread of the population in Canada, you can infer that what these rates might be, but especially if you have no context, if you're not familiar with the population distribution, these numbers alone aren't particularly helpful. It's much more informative to look at the rate. And then you will see that based on the total numbers and accounting for the population, the Northwest Territories is currently experiencing a crisis that is not visible when you look at this number. And that's because the NWT has a population of like 50,000, maybe. You can also see that Saskatchewan comes up as having a very, very high rate, right? Saskatchewan surpassed Alberta in terms of like the severity of their COVID crisis, but if you look at the total counts, your eye goes to Alberta. And similarly, right, looking at, say, the moving average of 7-day totals versus the just count of an individual value. I guess they don't. You can compare the 7-day average to the their data portal is not all that great, but the point being that the individual daily case totals have fluctuations and spikes due to, say, what's going on at the labs, if it's a weekend, things like that, right? So sometimes it's better to aggregate over a 7-day period to get a rolling average. So scaling can just allow us to get things into a different unit so it's more meaningful, right? Something per number of people or per unit area. It can also help us account for confounding factors. So a confounding variable is just something that's going to impact another variable. These values can hide or mask patterns of interest. So we've done this in lab a couple times, right? Even back to module 2, we calculated population density, right? The area of the census unit is a confounding variable of the population. Confounding does not mean that they're correlated. They can be highly correlated. So for instance, income and food have a strong correlation, which we're working with in lab this week. But population and shape area don't exhibit much of a correlation at all. So this is what happens when you plot population and shape area, right? The R-square value is 0.00038. There's no relationship as far as this very simplified model goes. But we know intuitively that the amount of area in a region, the size of that region, is going to have some influence on its total population. Now, just one other thing I want to point out. You can click this button to do some transformations. Logarithmic transformations, a kind of complex idea, but basically you're scaling things by tens rather than ones, and it allows you to pick up different patterns. There's still no relationship, it doesn't impact that, but it makes it a little easier to interpret this y-axis. right? But there is no relationship between total population and size of these census subdivisions, right? But again, that's partly because nearly the entire province is very sparsely populated rural areas. And also there's like not really any concrete rule behind the sizing of these units, right? It's a little bit arbitrary and all that. So population and shape area are not strongly correlated, but shape area is a confounding variable that we need to account for when doing many different types of analysis. Conversely, the amount of money that people spend on food is very highly correlated to their income. I don't think that's particularly surprising if people buy more expensive shit. So it's obvious here looking at this why you would want to normalize to account for that, right? Whereas it's not necessarily immediately obvious just looking at that plot of shape area versus population, right? And so if you leave income on the y-axis and you change this to income on food, you get a very different relationship, which I think intuitively makes sense. As your income increases, the proportion of your income that goes to food decreases, even though the amount of money you spend on food increases, because you can only eat so much, even if it's a really fancy steak. So if a really rich person has a bunch of extra money, they're not going to spend it all on food, they're going to waste it on other bullshit. So the point is that just because something's a confounding factor doesn't mean it's going to be correlated. It's not always going to be immediately obvious just looking at a plot that they need to be accounted for. Also, kind of the flip side of that, just because things are correlated doesn't mean that you need to normalize that data by that variable, right? So there are definitely circumstances where it would be ill-advised to normalize one variable by another just because they're correlated. And you may have heard this phrase, correlation doesn't imply causation, right? Just because there's a relationship on a plot doesn't mean there's a relationship in the real world. So choice of whether to normalize and what to normalize by can be informed by looking at descriptive statistics and things like that, but it needs to be a bit more like thought out and logical and governed by the context of what you're thinking about. And we can also have multiple confounding factors. And in this case, it can be a bit more difficult to think through. You can normalize by multiple variables. You can normalize by one variable and then divide by another. A good example of something that has multiple confounding variables that you really need to think about rather than just looking at, say, the chart of COVID case counts by age demographic, right, like Oregon did. There's confounding factors here, right? So yes, the younger demographic groups, 20 to 29, 30 to 39, have the highest number of COVID cases. But this is just a raw count. It's not accounting for a differential population membership of these age groups. So the 20 to 25 age group is overrepresented in BC's population, partly because of like international students, or not just like college students in general coming from elsewhere. So that would be something that you need to take into account. Although looking at the population differentials alone is not enough to like explain why the differences would be present. If you calculate COVID rates by population, by age group, you'd still see a pattern like this, but then there's other things that aren't necessarily always as easy to take into account. You can't just divide by a number. So workforce participation rate among these younger age groups relative to these older people who are retired and sit at home and don't have to interact with people, right? And on top of that workforce participation, what's the occupational exposure, right? Like a lot of the younger demographic groups are in service sector, customer-facing occupations where they come into contact with people. A lot of the younger people are in the medical profession, nurses, and things like that, right? And so this is more meant to just highlight the fact that like it's important to think about these confounding factors, not that you can necessarily always take them into account just numerically, but it's an important thing to think through logically as well. And lastly, we can standardize things so that we can more directly compare between variables that are in completely different scales. So I'll show you how to do this in just a moment. Box plots can be used in ARC to compare multiple different factors. And so what scaling does, this is just an example where you take the raw data, you subtract every variable or every point in that data set by its mean, and then divide it by the standard deviation. And you get something called a z-score, or a standardized value. And that goes back to this here, this normal distribution. In the red would be plus or minus 1z, in the blue would be plus or minus 2z. And so we can do this with box plots in ARC if you want. Box plot. So if you just have one value, then it's just going to show you the actual values that you're looking at. But you can add multiple, right? So say you also want to look at income, then it will scale those. Notice the differences between urban and rural for income and for food are pretty similar. And then you want to look at income on food as well. And we see a bit of a difference where urban dips below what we would expect. So this is just to point out that you can string together multiple variables in a box plot to get more information than you otherwise would have. So with that said, I just want to talk about the actual classification method. So broadly speaking, there's two types: supervised and unsupervised. So unsupervised classification methods are truly unsupervised. It's not like you just left a computer in a room and it's going to do this on its own. You do have to give some input. One, you have to choose what kind of unsupervised classification method you're going to use, but there's at least a little bit more input than you need to give them out. You normally need to say how many classes you want to look at. So some of the most common examples that we'll use in ArcGIS, or the common examples that are available, I'll talk through these and then I'll pull them up and display them. Equal interval, this is the simplest classification scheme. What it does is it just takes the range of the data, so that's the maximum and the minimum. You tell it, I want 5 classes, and it's just going to split that into 5 equal bins, regardless of what any other aspect of the distribution is. So even though it's defined by the data, it's only defined by 2 data points, the maximum value and the minimum value. And so in nearly every circumstance, you want to avoid using equal interval. It can be useful to just like get a quick look at it. But if you're like making something production quality, you'd be hard pressed to find a justification for using this one. The flip side of that is defined interval, where you say, okay, I want intervals this wide. The algorithm will then take the range, maximum and the minimum, and split it up into a certain number of classes based on the defined interval. Again, generally speaking, there aren't many circumstances where you want to use that. Moving up in complexity, we've got something called quantiles. So this is informed by the distribution of the data set. It's looking at percentile values. So if you want 5 classes, that will break the data into 0 to 20%, being the lowest 20% of the data, and then 20 to 40% being the next highest 20% of the data, 40 to 60, 60 to 80, 80 to 100. So one of the advantages of this method, the quantiles, is that it's not strongly influenced by outliers. So it's what you do is you order the data from lowest to highest, and then you split the percentiles based on where they're ranked. Then we've got the natural breaks method. This one is a bit more complex. Splits the data using something called the Jenks algorithm. I'm pretty sure this links to a Wikipedia page on it. So basically, yeah, you don't need to read this or worry about it. If you're interested, go for it. It's a complex method that seeks to optimize the splits in your data set into natural classes. So it lets the data kind of define how it wants to be grouped. Basically, the goal of the algorithm is to maximize the similarity within groups while maximizing the dissimilarity between groups. And so I had you all apply the natural breaks to figure out the classification for the NDVI in Module 3, for instance. Right, so we just took the data and said, what does the data say about itself? Right, what does the grouping or clustering show us? And then we've got the standard deviation. So this is a distribution-based classification method, which basically shows how far values are from the mean in standard deviations. So this method can be really useful for a trained user to figure out some patterns and trends in their data set, but it is not accessible to the broader public. Most people, if you were to just randomly survey folks on the street, aren't going to have a good idea of what the standard deviation means, right? One thing to note, the standard deviation classification method converts data to an interval class. So whether it's initially in interval or ratio data, it's looking at deviations above or below the mean. The mean is going to be the 0 point of that data set. So you generally want to use what's known as a diverging color map. I think I talked a bit about that in lecture on Monday. But diverging color maps are a good choice for interval data because it uses two separate colors, so like a red to blue gradation, to convey the fact that something is above or below, right? So we've got three different types of color maps we can work with. Sequential, which is good for gradations. It uses gradations of one color. It's good for showing increasing intensity of a thing, whereas diverging is good at showing the spread around something. I also talked about, say, the importance of making accessible color maps. When you're using a sequential color map, you never have to worry about it because it's always gradations of the same color. And so looking at shades or darkness, color blindness doesn't impact that. But when you're working with diverging color maps, about 4.5% of the human population can't distinguish between the colors red and green. So chances are at least one of you in the room has trouble with this one. You can filter by colorblind safe palettes, and that'll give you a better option. Anyway, so just to look at how these different classification schemes impact what we see on a map. I'm just going to walk you through applying a few of them. So right now, ARC usually defaults to the natural breaks. I feel like Esri might have even been the ones that created this algorithm. I don't know, but they seem to like it a lot. Also, just a little tip: when you're here, it's got help page. It's always helpful to like just read the description, right? But you can also view the histograms when you're looking at your data. This is useful when you're trying to decide on a classification scheme. One other point that I do want to make is, generally speaking, when you're trying to classify data, It isn't always doable, but this is a rule of thumb. You want to keep it to 5 or less. The more classes you have, the more colors you have to distinguish between. Humans tend to have a difficult time distinguishing between more than 4 or 5 colors. You can see even here, like these, I'm not a fan of their default color maps. The reds look pretty similar. If you use a color map that has more variability, sometimes you can get away with more classes, but even just for simplicity's sake, the point is to simplify your data. Try to keep it to 4 or 5 unless you have a really good reason to do that. So let's do it with 4. So this shows us one thing about the data, right? We're looking at income on food, but if we change this to population, it's going to group it in a very different way, right? Nearly the whole province is going to be grouped in here. So population is a really skewed distribution, if you remember the histogram that I showed. So if we change this to, say, equal interval, there's a really, really, really bad classification method to choose in nearly every circumstance, but you can see like why it's not very good for a population, right? Like why is a population of 170,000 in the same group as a population of 10? So you can see why equal interval is not very good. Quantiles has another very different impact on the data set. Remember, this one orders everything and then splits it based on percentiles where they fall in the ranking, right? And so basically what this is going to result in is the same number of shapes in every single class, or approximately the same. If you have an odd number, it might not split it perfectly. Or if you want to change it to standard deviation, you'll have deviations above and below. And so we'll look at a different value because population is only so informative, right? So these are deviations above and below the average, for instance. And if you change this one to quantile, you'll see this provides a more reasonable pattern to look at. So quantiles and natural breaks are usually your best 2 bets for displaying things, unless you have a reason to do things differently, which quite often you might find you do. So for instance, in lab this week, we're applying a manual classification. I'll talk about that in just a moment. I would like to say there's plenty more complex methods that like we're not going to apply in this class, but it's important to know that like there are methods for classifying multidimensional data sets, for instance. So this GIF is just showing something called a k-means algorithm. All you do is say, I want this many classes, and you give it a data set with as many variables as you want, and it's going to classify it for you. It just uses random iterations to try and find the best solution. There's other methods. This one called median absolute deviation. I use this to find outliers in data sets. You don't need to worry about like what it is. I'm not going to ask you about median absolute deviation on a test or anything like that. But it's just important to know that there's like more complex options out there. So those are just some of the unsupervised methods. Again, it's not purely unsupervised. You have to make the choice of classification, and you have to decide how many classes you want. So it's more like minimal supervision. But then we've got supervised classification. And so this, instead of letting the data define the splits, we, the user, define the splits. So we explicitly define our classes, or we provide a set of classes as training data. So, and this isn't to say that it's entirely human done. In many cases, the computer still does most of the work. So what we used in lab this week is a purely user-defined method, right? We applied the Stats Canada descriptors for rural, small population, medium population, and large population size. And so that classification scheme is not informed by the data necessarily. I mean, it's informed by the data in the sense that I'm sure they looked at a histogram before they created it, but it's more, what do these values mean in the real world, right? So that population density value of 400 was explicitly chosen to try and differentiate between a city or a town and something that's more spread out. And then those values of 30,000 and 100,000 for differentiating between small, medium, and large were also chosen to distinguish between a large city like Vancouver or Burnaby or a smaller city or municipality like Nanaimo or something like that, right? And so this was explicitly user defined, and all you had to do was open the attribute table, right click, select, apply. And so there's plenty of circumstances where you might want to use manual breaks. There's plenty of circumstances where there's not just like a table that you can look up and say, what is this? Where you still want to apply manual breaks. You, the map maker, have a lot of leeway to create your own classification schemes. You just want to be able to have some reason behind why you chose it, why you defined it. Oftentimes, a good strategy might be to, say, do a natural breaks or quantiles-based classification. But many times, when you do these types of classifications, you'll see that the break values have all these decimals behind it. You can edit it, change it to be something that it has more meaning or is easier for quick understanding, right? So you see these values are like 14, 16, whatever. Like, say you want to change it so it's nice round values, 15, 17 and a half, 20, not round, but like things that are quick and easy to interpret, right? Say you're trying to map rental cost in Vancouver. Your choice of classification might depend on who your target audience is. If you're trying to map out affordable housing for students, you might choose break values of $750 a month, $1,000 a month, and then just above that, right? If you're trying to map like housing for families, then you would use different break values, right? They're going to be expecting to pay different rents. They're going to have different resources. It's a different target audience. So you just need to think through all that. And as with the unsupervised classification, there's much more complex methods that you can generate. So we can just explicitly manually do the whole thing ourselves if we create, what we did with the Stats Canada. But in many cases, especially when working with data that's got multiple dimensions to it, that won't work. Instead, we can take a set of training data, some classes, and we can feed it to an algorithm. So we define the training data. We don't necessarily define the boundaries that explicitly create that data or that class. We define the training data, and then we feed it to a decision tree, for instance, and it can make the decisions for us to try and minimize the error in that training set. You can train an algorithm, and then you can use it to extrapolate or project to other values. Now, one decision tree isn't necessarily always the best. Sometimes you want to create a whole bunch of decision trees and then average them together. So this is known as a random forest. It's a really, really powerful method. It averages together a whole bunch of different decision trees to generate an output. So I showed this example of annual NDVI values for my field site. I think it was last week or the week before. I can use a decision tree to take those 8 years of data, apply it with some training points. So I define some training polygons that represent different classes of landscape within this area, train the model on just those areas, and then once the model's trained, it can be extrapolated to the broader region. Again, I'm not going to have you do this. It's a bit above pay grade of this class, if you will. But it's important to be aware that there's lots of complex methods, and that even though something's a supervised method doesn't mean that we're doing all the work. Even beyond that, neural networks, for instance, these are sometimes AI, you'll hear that thrown around a lot, artificial intelligence, machine learning. I do a lot of work with neural networks for my research. This is just a quick example of a network that is trained to recognize handwriting, right? And so you feed it certain characters, it learns a pattern off a training set, and then you can give it unique things that it wasn't exposed to, and it will try and fit them into a class. So there's one more thing that I want to open up. So we can apply all those classification schemes, natural breaks, what have you, to vector data, right? You're doing that in lab, or you're applying manual classification to the lab. I showed you some examples of how you can apply those different unsupervised classifications to a vector data set, but you can also apply it to vector data using the reclassified tool. Remember, we did this in Module 3. And so this is the landscape classification that I generated for my field site. If you turn all these layers off, you can see that there's a couple different types of terrain here. We've got a river and lake. We've got some very green vegetation. We've got, zoom in a little more. There's two kind of key types of vegetation here. One is, I showed a video of this area. It's like called polygonal tundra. And then there's further in the center an area where the permafrost has started degrading, and we've got ponds that have formed. Anyway, this is just the NDVI values for that site, averaged over the 8-year period. So these simple natural breaks, equal interval quantiles, they can't work with multidimensional data. They're just for one variable. But this is what happens when I train a random forest on 8 years worth of data. Fairly good classification scheme. This is what happens if you do natural breaks on the average of the data, right? So this scheme does a great job of highlighting the water features as distinct from everything else. It also does a pretty good job of highlighting the river levees and the upland terrain that has greener vegetation, which comes up on this image. But it doesn't distinguish between the two types in the center, which are an important distinction for what I'm researching. You can do the same thing with the quantile method. It does distinguish between the greener vegetation, the polygons, and the degraded landscape, but it groups all of the water areas in with that as well, right? Because this is looking at the total number of pixels within that image and making a classification call based on that. And then this is what happens when you try and use an equal interval method. So all this to say, basically, there's lots of different ways that you can classify data. There's lots of different choices of classification. As is going to be the answer to almost everything here. There's no one right way to do it. There's definitely wrong ways to do things, but there's usually no one correct answer. There's usually multiple options for you to work with. The most important point is to just think through the classification that you're applying. Have a good reason for doing it. If somebody asks you why, you don't want your answer to just be because that was the default that ARC came up with, right? You want to have some thought out reasoning behind it. Oftentimes, it's best practice to try out multiple different classification schemes, and then that can help you decide on which specific one you want to apply. So, yeah, that's it for this module. This one's pretty short. I hope this week's lab isn't too taxing on anyone. I tried to make the video instructions kind of quick. I know it's just a 1 week turnaround, but like part of the reason I didn't know how to make a map. Oh, one last point, I guess. Another part of the reason we're not making any maps for this week is because we're trying to show the whole province, and when you do that with really small data points, it doesn't lead to a good visualization. Classifying, simplifying things, making a bar chart or a box plot, you can take a whole bunch of data and display it more concisely in a small space. So that's another reason why it's useful. Anyway, all right, I'll let y'all go.